We're continuing our study of logic in section 3.3 on the conditional and biconditional. Back in section 3.1, we learned that truth tables are used to list every possible way that a simple or compound statement can be true or false. The next of the 5 basic truth tables that we're developing, this will be number 4, is called the conditional, sometimes called the if-then. The truth table for the if-then has only one case where the result is false, and that is if the P is true and the Q is false. This is probably the hardest one to remember, but it's the only false case for the conditional. T is true, F is false. T implies false is false. All of the other cases are true. So even though it's probably the hardest to remember, you have to focus on the one false case and just remember that the others are true. You might say this in words: a conditional is false only when the antecedent, sometimes that P is called the antecedent, is true and the consequent is false. Antecedent is the P and consequent is the Q. For example, if I gave you the statement, "If you need help, then I will help you," this compound statement is false only if the antecedent is true and the consequent is false. If you need help, then I will help you. You need help is false. I will help you is true, produces a false compound statement here. It's the only case where it's false. Now we're up to 4 of the 5 basic truth tables we will need to complete our study of logic. We started out with the conjunction and disjunction. In section 2, we added the negation. Now we're adding the conditional. The 5th one is called the biconditional. Notice that the conditional is an arrow pointing to the right. The biconditional symbol is an arrow pointing in both directions, or a double-headed arrow. The biconditional is only true when P and Q have the same truth values. In other words, they're both true or they're both false. So if you look at the truth table for the biconditional, it's only true if you get P true, Q true, or if you get P false, Q false. Otherwise, it's false. That gives us all 5 of our basic truth tables. This is sort of a visual summary with the memory aids below them. We've got the 5 truth tables. Rather than memorizing them line by line, my suggestion is to learn the memory aids or create your own memory aids so that you can remember what these tables result in without having to memorize them line by line. For the negation, I would say the memory aid is T changes to F, F changes to T, or you might say the negation changes the truth values to their opposites. However you want to phrase that memory aid so that you can remember it. For the and, the memory aid is it's only true if they're both true. For the or, the memory aid is it's only false if they're both false. For the implication or the if-then, it's only false if P is true and F is false. To me, that's the hardest one to remember. And finally, the biconditional, it's only true if P and Q match. However you want to rephrase those memory aids, there are 5 of them, and you need to be able to say them to yourself so that you can produce those tables if you need to. I referred to some of our work as working in the interpretation mode. These are your tools for working in the interpretation mode. Now let's see if we can take some more complex logical statements and apply what we've learned here to those statements. Sometimes we actually need to leave interpretation mode and move to translation mode, and this is when we need to translate from logical statements to English statements or vice versa. So let's practice that a little bit. Recall that statements of the form P implies Q are called conditional statements. Again, the implication, the arrow pointing to the right, has various names. Sometimes you call them if-then, you can call it an implication, you can call them conditionals. Conditional statements can be written in the form if P then Q. Sometimes the word then is left out. If P, comma, Q. It just means that in English language sometimes you leave out the word then, but it's understood to be there. For instance, all the following are conditional statements. If we order pizza, then we can have it delivered. If you go to the movie, you will not be able to meet us for dinner. If n is a prime number greater than 2, then n is an odd number. You don't actually have to have the word then in there for it to be understood to be there. In any conditional statement represented by if P then Q or by if P Q, the P statement is called the antecedent, as I've mentioned earlier, and the Q statement is called the consequent. Occasionally you'll see the word antecedent called hypothesis and the Q called the conclusion. So, identify the antecedent and consequent in the following statements. If our school was this nice, I would go there more than once a week. The antecedent is the P, our school was this nice. The consequent is the Q, I would go there more than once a week. It's just that simple. If you don't get in that plane, you'll regret it. You don't get in that plane is the antecedent. You'll regret it is the consequent. This is just a summary now of what we've said. Sometimes that right pointing arrow is referred to as the arrow notation, but basically otherwise that is just a statement of what we've already said. The conditional statement, if P then Q, can be written using the arrow notation as P with the right pointing arrow, Q. The arrow notation is read if P then Q or P implies Q. And remember, the truth table for the conditional, it's only false if P is true and Q is false. Make sure you get that one right, because at least for me, that's the hardest one to remember. That's the only case where the implication is false. I like to think, sometimes I want to make sure I'm thinking about it right. I'll make up a simple sentence. For instance, if I said, if you need me, I'll be there. Think of it this way. If I said that to you, the only time my statement would be false is if you needed me. That would be like P being true, but I wasn't there. That's like the Q being false. If I said, if you need me, I'll be there, but you needed me and I wasn't there, that would be a false statement. And it's the only time an implication is actually false. Now let's play around with this implication and the conditional notation and do a truth table that involves that. First of all, I like to add intermediate columns. So I'm going to push that off to the side and build my own table where I have intermediate columns. Now we've talked about this in earlier sections. You notice that if you look at the pieces, there's a not R piece of this compound statement. So I'll make a not R column. There's also a Q and not R piece. So I'll make a column for that. And then of course you want a column for the final statement as a whole. So I will take that original truth table and add these columns to make it a little easier to work through the way I've been doing it. Now that I've done that, let's get started. The first thing you want to concentrate on is the not R column. You have the R columns. All you have to do is change the truth values to their opposites and you'll have the not R column. Then you want to go to the next column, and you notice in the next column you have a Q, but you know the values of Q from the second column, so you move those over under the Q. Same thing for the not R. I just produced the not R column, so if I copy that underneath the new not R, I have that, and then I notice there's an and between those two. Now I have to evaluate this and remember the shortcut for the and, the memory aid for the and, is it's only true if they're both true. So if you scan down there, you just look, and every time you see a true and true, you change it to true, and unless it's a true and true, it stays false. So I'm just scanning down here, and I'm not seeing many true and trues. There's another one, true and true, it's true. But until I see a true and true, it's false. And finally, I'm ready to tackle the last column. The last column begins with a P, so I'll take the P values from the far left column and move them over. And on the other side of the implication symbol, I have that Q and not R, so I'll take that column of values and move those over. And then I note that I have an implication symbol between them. So I have true implies false, true implies true, and all the way down the list. And you have to remember, for an implication, there's only one false case, and that's if the hypothesis, I said it's sometimes called the hypothesis, the antecedent, whatever you want to call it, and the conclusion is false. If the hypothesis or antecedent is true and the conclusion is false, then the statement is false. Otherwise, it's true. So if you scan down the list, you're actually looking for true implies false. Well, the very first one is true implies false, so that's false. But that's the only one you're scanning for that turns false. If it's not true implies false, then it will be true. So it's true here. There's a true implies false, so that's false. There's another true implies false, so that's false. That's not true implies false. That's not true implies false. That's not true implies false. And that's not true implies false. So as you scan down the list, you're looking for true implies false. That particular thing is false. The rest of them are true. And voila, you have the truth table completed. There are two more special cases that we need to know. Remember, in the last section, we talked about two cases being the two De Morgan's laws. Here are two more special cases that involve the implication. This has to do with taking conditional statements and putting them in an equivalent form. By examining the two truth tables below, we see that not P or Q and P implies Q are the same values. I'm not going through this again, but if we went through the process of doing the truth table for not P or Q, which is the one on the left, and then we did the truth table for P implies Q, which we just did actually, on the right, you notice they have exactly the same truth values. The shaded column on the left truth table is true, false, true, true, and the shaded column on the second truth table is true, false, true, true. So they have exactly the same truth values. That means that those two forms are equivalent to each other because they produce exactly the same truth values. So what I've shown is that the conditional P implies Q is equivalent to the disjunction not P or Q. And we tend to use this symbol in the middle, not an equal sign, but three horizontal bars as being the word equivalent. For our purposes, we're not making much of a distinction, equivalent, equal, but technically that three-bar symbol is equivalent. So P implies Q is equivalent to not P or Q, and I know that because I looked at the truth tables back over on the left and saw that they produce the same truth values. So that's the first of the new special case rules that we need. Let's practice this. If I ask you to write in its equivalent disjunctive form this sentence, if I could play the guitar, I would join the band. Now what they mean by disjunctive form, if you're looking up at the formula, on the right-hand side there's an or, and an or is a disjunction. So that's what they're referring to. But anyway, back to the problem. If I could play the guitar, I would join the band. The I could play the guitar is like the P. The I would join the band is like the Q. So I'm taking that statement, which is modeled on the left-hand side of that formula, and changing it to the right-hand side. So right now, I've got the left-hand side of the equation done. I want to change it to the right-hand side of the equation. So I form not P. Well, if P is I could play the guitar, then not P is I could not play the guitar. Or Q, which is I would join the band. So the statement I could not play the guitar or I would join the band is logically equivalent to the statement that I started with, which says if I could play the guitar, I would join the band. So that's a simple example of using this equivalent form of a conditional formula. I'm not going to go through this, but we could show that the negation of a conditional can be written as a conjunction. A conditional can be written as a disjunction, an or. The negation of a conditional can be written as a conjunction, which is an and there's the formula. I derived the other one, or at least I showed that it was true. I'm not going to do that here, but it would be just as easy to do as the other. We just take it for granted. An example, write the negation of the following statement. The statement is, if the lines are parallel, then they do not intersect. So the negation of that statement The lines are parallel is like the P. The if-then is the right pointing arrow. They do not intersect is like Q. So forming the left-hand side of the statement and changing it into the right-hand side of the statement is what they're asking me to do. The P is the lines are parallel. The conjunction is the and not Q would be, if Q is they do not intersect, then not Q would be they do intersect. So the negation of the original statement, if the lines are parallel, then they do not intersect, is the lines are parallel and they do intersect. And that's an example of the second of the special formulas that we were introducing right now. Now recall from our earlier discussion that statements of the form P with the double pointing arrow, the double-headed arrow, are called biconditional statements. And the truth table of the biconditional is given here, and the key to remembering it is it's only true if they match. If they're both true, the biconditional is true. If they're both false, the biconditional is true. Otherwise, it's false. And the memory aid is it's true if and only if they match. An example, construct a truth table for the statement P if and only if not Q. And by the way, when you say biconditional, in that double-headed arrow, you say if and only if. So P if and only if not Q. So I'll build my truth table, and as we've done before, adding a preliminary column for that not Q that appears as a piece of the final statement. So I begin my work by taking the Q and changing it to not Q. So I change all the truth values in the Q column to their opposites to get not Q. Then I look and I notice in the final column I have a P on the left of the if and only if symbol. So I'll move those P values from the far left underneath the P. And then on the right side of the biconditional symbol I have the not Q. So I'll move the not Q values underneath. And then I notice that the symbol is the if and only if, the biconditional symbol. And then I've got to remember that the memory aid for biconditional is it's only true if they match. So you're going down and scanning and looking for matches. True if and only if false is not a match, so that's false. True if and only if true is a match, so it's true. False if and only if false is a match, so that's true. And false if and only if true is not a match, so that's false. And there's your truth table. This is again a visual aid to let you see all 5 of the truth values so you can remember these, and underneath them you have the what I call the memory aids. With the negation, you switch the truth values. True becomes false, false becomes true. For an and, it's only true if they're both true. For an or, it's only false if they're both false. For an if-then, it's only false if P is true and Q is false. And for the biconditional, the if and only if, it's only true if they match. And then we've added these special cases. From Section 2, we had De Morgan's laws, and from our just immediate discussion, we added 2 more from Section 3.3, and those are the equivalent disjunctive forms of conditional and the negation of a conditional, which puts it into conjunctive form. In other words, disjunctive form is the one with the or, and conjunctive form is the one with the and. So this page summarizes pretty much the basic tools for sections 1, 2, and 3. Let's do another example with the disjunctive form of conditional. What if I ask you to write the conditional in its equivalent disjunctive form? If x is an irrational number, then x is not a terminating decimal. Just proceed as before. The x is an irrational number is the P. X is not a terminating decimal is Q. So you want to take that and turn it into the right-hand side of the equation, which says not P, x is not an irrational number, then the disjunction, which is the or, and then the Q, which is x is not a terminating decimal. So you put not P ored with Q, and you get the statement, x is not an irrational number or x is not a terminating decimal. Simple enough. If you wanted to add the word either to make it sound a little bit better in English, you could. So if you wanted to make it sound maybe slightly less stilted, you could add the word either in front and say either x is not an irrational number or x is not a terminating decimal, but that's optional. You don't have to do that. Now let's do another example with the negation of a conditional. That changes it into conjunctive form, in other words, to something with an and. What if the statement were, if pigs had wings, pigs could fly? Again, P would be the statement pigs had wings, Q would be the statement pigs could fly, and you want to change it into the right-hand side, which is P and not Q. Well, P is the statement pigs had wings, so you just write that down. The tense doesn't much matter. It might sound better as has or have instead of had, but otherwise that's not really important. But the important part is that you've got to get the and. The conjunctive form produces an and between the statements, and the last statement is the negation of Q. Q is pigs could fly, so not Q would be pigs couldn't fly. Or again, you're not worrying too much about the tense exactly. You just want to make it sound a little better. So you might say something like pigs have wings and pigs can't fly. Not worrying too much about the tense of the verbs. You could change it even to something like this. Pigs have wings and they can't fly. The exact wording is not important. It's the structure that's important and the meaning behind what you said. We talked a little bit earlier in the previous section about the way that WebAssign presents some of these truth tables. So I want to go back to a problem with the conditional and biconditional that presents the table like you'll see it in WebAssign. And here's an example. They're asking you to complete the truth table for this compound statement involving a biconditional. You start off, as you always do, with the simple stuff. You have a Q column which you want to fill in, so you take the Q values that you already know about and just move them underneath the Q. Then you move over to the not P, so you're going to look at the P column and change all the truth values to their opposites, so the true becomes false, the true becomes false, the false becomes true, and the false becomes true. Then you've got to realize you're working with an and. So the trick for and is that it's only true if they're both true. True false is not both true. False false is not both true. There's a true true, it's true, and the last one is not true true. So there's only one true in that set, and that's the true implies true. Anything else for an and is false. And remember, we talked about this before, once the Q and not P column have been used to produce the and column, those shaded columns are essentially used up. You're only paying attention to that circled column under the and. Then you move over to the other side and you're going to put the not P in. So you go to the P column and you change all the truth values to their opposites. True becomes false, true becomes false, false becomes true, false becomes true. And notice I've shaded the column under the and because, as I said earlier, the Q and the not P produced that and column in the middle, and so they've been sort of, in some sense, used up. So you don't pay attention to those two columns anymore. You're only interested in the and column on the left side of the if and only if, and the not P column on the right side of the if and only if. And remember, for an if and only if, a biconditional, it's only true if they both match. You notice the very first case, they're both false. That's a match, so it's true. Second, both false, they match, that's true. The third one, both true, they match. The fourth case, false and true, they don't match. So the only false is the very last row. The others are true. And there's the truth table for the compound statement. Let's practice a few more things. Is this true or false? 5 equals 8 if and only if 6 is equal to 4. Remember, this is an if and only if, which is the biconditional. It's only true if they match. If you go back up and look at this statement, 5 equals 8 is false, 6 equals 4 is false, and the if and only if is the double-pointed arrow, or the double-headed arrow, and they do match, so the statement would be true. Another example. This one has a little twist to it. True or false, assuming x and y are real numbers, 2x minus 1 is equal to 11 if and only if x is equal to 6. Now this is still a biconditional, but the best strategy when you have variables in these things is probably to go ahead and solve for x when they're not solved for x. So I would say take that 2x minus 1 is equal to 11 and say, well, add a 1 to both sides and divide by 2, and you end up with x equals 6 if and only if x equals 6. Now, obviously, they're going to match, right? Because you've got the exact same thing on both sides, so how can they not match? It's easy to see that those left and right-hand sides are going to match all the time. If x is equal to 6 on the left, it'll be equal to 6 on the right. If it's not equal to 6 on the left, it will not be equal to 6 on the right. So they will match each time. So even though there's a variable in there, I can see that the left and right-hand sides will match no matter what the value of x is. So the original statement is definitely true. Let's look at this one. Is the given biconditional true or false, assuming that x and y are real numbers? The biconditional says x squared equals 4 if and only if x is equal to 2. Now there are two cases to check depending on whether the statement x squared equals 4 is true or false. So in case 1, we can assume that x squared equals 4 is true. Now if x squared equals 4 is true, we want to know about what that implies about x being 2. Remember, a biconditional is only true if the truth values of the left statement and the right statement match each other. So if the left statement, x squared equals 4, is true, then in order for the biconditional to be true, then the right statement, x equals 2, has also got to be true. But think about that. If x squared equals 4 is true, do we know that x equals 2 is true? Think about that a minute. If x squared equals 4 is true, is x equal 2 true? Not necessarily. If x is equal to 2, then x squared is equal to 4. That is a true statement. But if x is equal to minus 2, which would mean x equal 2 is false, x squared is still equal to 4. That would still be a true statement. So we don't necessarily know that x is equal to 2 just because x squared is equal to 4. That means we can't guarantee that the two statements match truth values, which is the only way that a biconditional is true. Because if x squared is equal to 4, all we know is that x could be 2 or minus 2, not just 2. I will say that there might be an easier way to think this through. When you have a problem with a variable in its a so-called open statement, it might be easier just to think it through without breaking into cases. And what I mean by that is, if x squared is equal to 4, we know from algebra that x is either 2 or minus 2, but the right-hand statement just says x is equal to 2. So we know that x could be 2 or minus 2, not just 2, which means we can't guarantee that the truth value of the left statement matches the truth value of the right statement. Therefore, the biconditional is false. So you might find it a little bit easier just to think about it that way. It's up to you. This is sort of a monster-looking thing, but it's no harder. It's just more work. So let's go straight for it. The first thing I would do is take that open P column and move the P values on the far left column over. Then I'd move over to the Q's and do the exact same thing. Move those Q values over. Then I would attack the implication. Remember the implication, it's only false in the true implies false case. So I'm looking for true implies falses to turn to false. Otherwise it's true. So I just scan down through there and notice there are only 2 cases that give me true implies false. So I'm going to call those false. There aren't any more of those, so the rest of them are true. So also, I said earlier, and I think I'll actually illustrate it here, that once the P and the Q are used up to produce the implication, they're essentially gone. So I'll actually shade them out just to emphasize that once the P and the Q is used to produce that value under the implication symbol, they're used up. They're not important in the table anymore. Next, I'll notice that I have an R column over there that needs filling in. So I'll take those R values and put them in. And I notice I have a not P column. So I have a P column. So to do a not P column, I just change them all to the opposites. All the trues become falses and all the falses become trues. And then I notice that I have an and between them. An and is only true if they're both true, and I scan through there and only see 2 cases where they're both true, so those will be the trues. Everything else will be false. And again, I've used up the R and the not P. By producing the and, I used up those other two columns. I'll actually shade them out just so your eyes don't focus on them anymore. And as I move across, I see that there's another R column, so I'll move those R's over. And I see there's a not Q column, so I'll take the Q column from the far left and change all the values to the opposites. All the trues become false and all the falses become true. And then I notice I have an OR. An OR is only false if they're both false. So if I scan down through there, I see two cases where they're both false. So that makes a false. Everything else will be true. And again, the R and the not Q column have been used up, so I'll sort of shade them out so your eyes don't focus on them anymore. Now I'm going back across here, and I notice I have to fill out this OR column. I couldn't fill it out until I got trues and falses on both sides of it, but I do have trues and falses on both sides, and I remember that an OR is only false if they're both false. So if I scan down through there, I only see two cases where they're both false. So I'll change those to false. Everything else will be true. Now those two columns got used up. Look at this one more time. I produced this OR column by using the two columns on the left and right, so they get used up. I shaded those columns out so that your eyes don't focus on it. So now all I have left is that implication, and on the left side of the implication, I'm looking at that one column that's not shaded out, and on the right side of the implication, I'm looking at the one column that's not shaded out, and I noticed that with an implication, there's only one false case, and that's true implies false. So I scan through there and find the two cases that have true implies false and make them false, and the rest of them will be true. And there you go, you have your truth table.